Okay, so in the last lesson, I was emphasizing that the most important thing about the moments of continuous random variables is that you should be able to, if you see an expression involving integrals, recognize it as expected value or a cumulative probability or a variance, that most of the time in your methods classes, you're not actually going to be needing to evaluate those integrals. Except in this lesson. In this lesson, we are going to integrate some PDFs to find the moments of a uniform random variable. And that is actually, it does have some uses that you might encounter outside of this class, more in formal modeling than in statistics. Statistics uniform random variables don't occur that often, but if you're taking a game theory class and you're trying to develop some kind of model of strategic behavior and you want to have some uncertainty in your model, lots of interesting strategic uses of uncertainty, the uniform random variable is a nice simple way to uh, add some uncertainty to a model if you're trying to see how the people you're studying react to it. Okay, so the random variable I'm thinking about here is just kind of a generic x distributed uniformly on the interval C and D. So I'm not even saying what the endpoints have to be. We'll remember from a couple lessons back that the PDF associated with this is 1 minus d over c for x between c and d, and it's 0 otherwise. Okay, so what we mean by a uniform random variable is that its PDF is flat over a certain range, and the height of the PDF is whatever it needs to be to integrate to 1. And so if the base of the rectangle shape that these PDFs always have is d minus c, the height needs to be 1 over d minus c in order to satisfy Kolmogorov's second axiom. That's what's lurking there. Okay, so I've got my PDF, and so now I want to use the formula from the last lesson, where we said the expected value of a continuous random variable is just the integral over the whole range, wherever it's not going to be 0, of x times PDF of x. Okay, so this is the kind of general thing. And now what I need to do is I need to put this PDF into my general formula. Okay, so for the uniform case, what that says is that the expected value of, we'll call it XU here, for uniform, give it that name, is going to be the integral from C to D. This is the only parts of the real line where the PDF is not 0. So there's nothing under the curve when the curve is sitting there on 0 of x times 1 over d minus c dx. Okay, so all the information from the PDF I've now put in my equation for the expected value. I've got the PDF here, and I've got the fact that it takes these values over a specific range reflected in my limits of integration, and now I'm just going to integrate that thing. Okay. So remember, when we evaluate an integral, what we're asking ourselves is, what is the function whose derivative is x times 1 over d minus c? Okay, so if we took the derivative of a function, what would that function have to be in order for this to be our answer? And just sort of reminding ourselves of how it works with polynomials. As you take derivatives of polynomials, the exponents decrease. So if you have a linear derivative here, that probably means you had a not probably, it definitely means you had a quadratic function to start with. And the derivative of x squared would be 2x. So the derivative of x squared over 2 is x. And this constant just comes along for the ride. So evaluating that indefinite integral, doing the antiderivative step here, gives me x squared over 2 times dc. And if we want to just sort of check ourselves in our head, taking the derivative of that, let's not even do it in our head. Let's do it over here in the corner. Check. So the derivative with respect to x of that baby, x squared over 2 d minus c. Okay, that is 1 over 2 d minus c times 2x equals x over d minus c. Yes. Okay. So I did the antiderivative part of finding my integral here. I still want to remind myself what the limits of integration are. So I'm evaluating this as x goes from c to d. And now taking that indefinite integral and turning it into a number that we would interpret as an area, we just substitute in the upper bound for the for x, and then subtract the lower bound substituted in for x both places. Okay, so substituting in my d, I get d squared over 2 d minus c, and c squared. Okay. So again, let me emphasize, I just substituted in d for the x, and then I subtracted off c, substituting for the x, the way we always evaluate definite integrals. Okay, so that's fine. That's an answer. I can't help noticing that we've got this difference of perfect squares up here, and that's something that one of our favorite things to factor here. So that in fact equals d minus c d plus c. Oh, look at that. And we get to cancel, yay. And we get d plus c over 2. That is the expected value of random variable uniform on the interval CD. And so that's interesting. Look what we got here. This is the midpoint. It's the point that is halfway between D and C. So if we had a case where C equals 1 and D equals 3, that midpoint would be 3 plus 1 over 2 would be 2, the point exactly in the middle. And that actually makes sense, right? If there's just as much probability mass on one side as the other, that's going to, this is the point that where they're exactly going to balance out. There. Okay. All right. So this is in fact the expected value of a variable that is uniform on the range CD. Good. All right, so let's do that same thing for the variance now. So the variance of xu is going to be x squared times the PDF minus the expected value squared here. Okay, well, this is cool. We just found this, right? This is d plus c over 2. We just found the expected value. We're squaring it. So fine, the second term, as always true, the second term of the variance we've almost always gotten from finding the expected value somewhere else, but now we have to find the, we have to evaluate this integral. The expected value of the square of x, or this first term in the variance. So same as we did, before. We'll substitute in the particulars of the PDF that we're working with, and then we'll take the antiderivative to get rid of the integral sign. So what do we got here? It's the integral x squared. That stays the way it is. X is just x. The only part that we're getting specific about is what is the PDF? What random variable are we talking about? No matter what it is, we're going to have to square it to find the variance. And so what we're substituting there is 1 minus d over c, and that is over the range c to d. So that's all the information that we're taking from the PDF with respect to x. Okay, so it's another one of these polynomials, and just as the integral of x is x squared over 2, we remind ourselves the integral of x squared is x cubed over 3. So x cubed over 3, the constant just comes along with us, and this is evaluated from c to d. And okay, so that's gonna need a little bit more working with here. I might as well go ahead as I'm going to the next line and write out the square for the expectation of x squared. So that's going to be d squared plus 2dc plus c squared over 4, and we're subtracting that whole thing. So I'm just going to keep the parentheses to remind myself that all these terms are going to get subtracted. Okay, so putting in the numbers to take my indefinite integral and turn it into a number here, that will be d cubed minus c cubed over 3d minus c minus, I'm not going to write it again, that whole thing there. So here's a less familiar factoring thing, but it is still true that d cubed minus c cubed is that I can factor here into d minus c plus, what's the other part of that? D squared plus cd plus c squared. And that is a factoring fact, not something that I'm expecting you guys to remember, but it is in fact true, and you can check it if you want. Okay, and I'm going to use this little fact here to simplify my first term, and then we'll combine terms. Okay, so that's going to be d c d squared plus cd plus c squared. And see, I'm really happy about that because that's going to let me, again, cancel terms. And I'll have my other expression, which is d squared plus 2dc plus c squared over 4, canceling. These guys go away. Okay, so looks like I'm just going to have to multiply through to put them over a common denominator here. So common denominator, I guess, is 12. So I'm going to multiply this by 4 over 4 and that by 3 over 3 to get my 12. So I'll get 4d squared plus 4cd plus 4c squared. This whole thing is going to be over 12 minus 3d squared minus 6dc minus 3c squared. I think I forgot a 4 here. That should have a 4. Okay. And okay, let's see if I can carve out a little bit of space here, because it's going to be, we are going to simplify here, although I am running out of space. So this here equals, okay, so I've got 4d squared minus 3d squared. That leaves me d squared here. And let's remind myself I took care of that, and I took care of this. I've got 4CD minus 6 DC, so that is negative 2 CD. And what else is left? I've got 4C squared minus 3C squared. That is going to be positive C squared over 12. Oh, look, and I can factor that too. That is D minus C squared over 12. And this is the variance of X uniform on CD. Okay. All right. So the algebra got a little tedious there. The board got a little bit messy. It got a little bit tedious. It didn't get a lot tedious. The main thing I'm wanting to show you here with the uniform random variable is that there's nothing more than integrals. A lot of the time, the integrals can be kind of hard to evaluate. That's how integrals are. The uniform random variable is kind of a nice one in that the integrals are easy, and all it is kind of going through the same basic steps, taking the integral, and then from here, taking the integral, substituting in the values to make it a number, make it a definite integral. And then everything from here on down was just algebra to put it into a nice, pretty form, which is what we get.